If I have like a matrix and I want to multiply my matrix times a vector, like I have a matrix A and I multiply that times a vector X, and my product is going to be a vector B, right? And so let's say that A is a 2 by 2 matrix, and so that means X is a vector with 2 entries, and then that means B is going to be a vector with 2 entries, right? So I could write something like 1, 2, 3, 4 times the vector 1, negative 1, and matrix vector multiplication tells me that this product vector is going to be negative 1, because it's the dot product of the first row and then this column vector, so it would be 1 times 1 plus 2 times negative 1. And then it would be also negative 1, because it would be 1 times 3 plus negative 1 times 4. Okay? So just a refresher, that's how matrix vector multiplication works. So if you see this word, it's pronounced eigenvalue. I don't remember what that means in German, but I know eigen is like a German part of a word, right? So eigenvalue in German means something like special value. And then also, there's another vocabulary word, eigenvector. In linear algebra, we would use the symbol lambda, the Greek lowercase letter lambda, to represent eigenvalues. And so we would write lambda 1 for the first eigenvalue and lambda 2 for the second eigenvalue. And then for eigenvectors, gosh, it's been a minute. I think we use nu to represent the eigenvectors, which looks pretty much like a V. And it obviously depends on what textbook you're using, like what convention the author wants to use. But lowercase Greek letter nu, which I think is just spelled N-U, looks pretty much like a lowercase v, and so it's hard to tell the difference. But that's what I'm trying to use as a symbol for eigenvector. So here's the definition of what an eigenvalue and an eigenvector are. If I have a matrix A, and I multiply A times an eigenvector, nu1, then this is the same thing as if I take my eigenvalue times the eigenvector, okay? Because this matrix vector multiplication is going to be a vector, right? So this would be like a two-dimensional vector, or a vector with 2 entries. And then on the right side, this is a scalar, because that's a value, that's an eigenvalue, so that's a scalar. A scalar times a vector, and so that product is also going to be a 2-dimensional vector, or that would also be a vector with 2 entries. Okay? So if A is a 2 by 2 matrix, then A, the matrix A, is going to have 2 eigenvectors, and it's going to have 2 eigenvalues. You can't have 3 distinct eigenvectors, and you can't have 3 distinct eigenvalues unless A was a 3 by 3 square matrix, and then you could have 3 eigenvalues and 3 eigenvectors, right? So the number of eigenvalues and the number of eigenvectors and the size of your square matrix are all the same number. There's several ways of finding out what the eigenvectors and eigenvalues are. Most of the techniques you use in practice are iterative techniques, but the boring way to do it is this. The boring way to do it is to say, okay, my matrix A is the matrix 1, 2, 3, 4. If I wanted to find an eigenvalue, right, so I'm going to write this equation here. I could subtract lambda nu from both sides, and I would have something like this. Right? I could factor out the vector nu, only it doesn't really make sense to have a matrix minus a scalar. And so if I wanted to, I could backtrack a little bit, and I could say that instead of having just nu there, I could call this I nu, where I is the identity matrix. So multiplying I times nu, that just gives me the vector nu. So I haven't really changed anything by doing I nu. But what this does for me practically now is if I say this, again, I nu is just nu, then whenever I factor out the nu, then I have lambda times the identity matrix. And that is a matrix, and I can actually do matrix minus a matrix. You just do the subtraction entry-wise. Corresponding entries, you subtract them. Okay, so now the idea is this right here is a matrix. And we are going to set the determinant of this matrix equal to 0. So if A is my matrix 1, 2, 3, 4, then this particular matrix is going to be the matrix 1 minus lambda, 2, 3, 4 minus lambda. And again, I'm doing the determinant of that matrix equals 0. And so if you remember the determinant, then this is going to give me 1 minus lambda times 4 minus lambda minus 2 times 3, which is 6, equals 0. If I multiply that out, if I try to expand it, I'm going to get lambda squared minus 4 lambda minus lambda, so minus 5 lambda. Plus 4 minus 6, so minus 2, equals 0. And so this is a quadratic equation, so I hope you guys remember your quadratic formula.
I have a question. What does it mean to, like, the multiplication of those two matrices gives 0? Does it mean A minus I?
You mean here?
B equals 0.
So this is a matrix and this is a matrix. So whenever I subtract them, it gives me a matrix, right? It gives me that matrix specifically.
Yeah.
But then I multiply that times the vector nu. And whenever I do matrix vector multiplication, the result's going to be a vector. And so this 0 is talking about the 0 vector. It's not just like the scalar 0, but it's a vector with 2 0 entries. I could write this and it would mean the same thing. Yeah. That's what I mean. Okay. Now, this would be 5 over 2 plus or minus the square root of 25 minus 4 times 2, 8. So minus negative 8 makes plus over 2. So square root of 33 isn't a nice number. But this gives me 2 values for lambda, and these are going to be my 2 eigenvalues of my matrix. Okay? So once you know your eigenvalues, you can again go back to these equations, knowing my eigenvalues, and you can solve for the eigenvectors by solving a system of like 2 equations. It's kind of a pain in the butt process. Okay? I'm not going to quiz you on that. That's not going to show up on an exam. I just want to show you what I mean when I'm talking about eigenvalues and eigenvectors. If you had a 3 by 3 matrix instead of a 2 by 2 matrix, you can still take the determinant of this kind of matrix, except taking the determinant is going to be even more excruciating calculation. And then your polynomial equation over here would be a cubic equation. And so that would be even more painful to solve. If you had a 4 by 4 matrix, again, the determinant's harder to take, and you would end up with a quartic polynomial equation. That's even more of a pain in the butt to solve. And so these problems get out of hand really fast if I tried to show you an example more than 2 by 2. But it's possible. So whenever you have a matrix, it's not necessarily possible for you to find the eigenvalues and eigenvectors, but it does happen with some square matrices. If it's not a square matrix, you can't do this. But if it is a square matrix, maybe you can. It's kind of like how some square matrices are invertible and others aren't. Some square matrices are diagonalizable and some aren't. And so if your matrix is diagonalizable, then you can find eigenvalues and eigenvectors, and if it's not, then you can't. And so that's something you would learn a lot about in linear algebra, and we would spend weeks developing this kind of theory if you were taking a linear algebra course, but we just don't have the time. If you were trying to look for the critical points of a multivariable function, you set the gradient of the function equal to 0 and you solve. That is true. That's still the definition of the critical point of a multivariable function for 3 variables, or 4 variables, or 5 variables, or 100 variables. That's still what we mean by the critical point. But if you want to characterize the critical point as a maximum or minimum or saddle point, what you have to do is you actually have to find the eigenvalues of the Hessian matrix. And then if all of the eigenvalues are positive numbers, you're looking at a maximum. If all of the eigenvalues are negative numbers, then you're looking at a minimum. But if some of your eigenvalues are positive and some of the eigenvalues are negative, then you're looking at a saddle point. So the trick I showed you yesterday, where you take the determinant of the Hessian, it turns out that only works for 2 by 2 matrices. It doesn't work for 3 by 3 matrices, so it doesn't work for functions of 3 variables or 4 variables. Like, practically speaking, for your exams, we will not do critical points or characterizing critical points for functions of 3 variables or 4 variables. You're not going to see this. We're only going to do characterizing critical points for functions of 2 variables. So that way, the determinant trick I showed you yesterday works, okay? It's going to work. The thing I showed you yesterday will work because I'm only going to give you functions of 2 variables if I ask you to characterize critical points.
So if we were to use the eigenvalue test to find those extremas, how for 3 by 3 matrices, how would we do it?
Put a long process.
Yeah. So if you had a function of 3 variables x, y, and z, okay? Then to find the critical points, you would set the gradient equal to 0, right? All the partial derivatives equal to 0. Then your Hessian matrix would be a 3 by 3 matrix with all of the second partial derivatives. And then what you would do is you would take the determinant of the matrix H minus lambda I, and you would set that equal to 0. And when you actually do this determinant calculation, the result is going to be a cubic equation. So you'll have a 3rd degree polynomial set equal to 0. And so if you find the roots of that polynomial, the roots of that polynomial are going to be the eigenvalues. There should be 3 eigenvalues of your Hessian matrix. So if those 3 eigenvalues are all positive, then you're looking at a maximum. If they're all negative, then you're looking at a minimum. And if they're all a mixture, some positive, some negative, then you'd be looking at a saddle point. In fact,
so in theory, we would have like the whole matrix.
I might be misspeaking even now, so let me double check something. So yesterday was 13.8. Let me just look at my notes and see this. So, okay, so I actually misspoke. So if all of your eigenvalues are positive, right, that's kind of like having a positive second derivative. And if you have a positive second derivative, then your function would be concave up, right? But if it's concave up, that means you have a minimum. Then if all 3 of your eigenvalues are positive, that means your function is going to be concave up, which means you have a minimum at the critical point. If all three of your eigenvalues are negative, that would mean your function is concave down, which would mean you have a maximum at your critical point. If your eigenvalues are some positive, some negative, then that means in some directions, on some traces, you're going to be concave up, on some traces, you're going to be concave down, and so you're looking at a saddle point. Okay. So one question you might have then is like, why does this determinant trick work for 2 by 2 matrices? In other words, why does the determinant trick work for functions of 2 variables, right? Why can I say this? It turns out that the determinant of a matrix is the product of the eigenvalues. Okay? So if you have a 2 by 2 matrix, the determinant of that 2 by 2 matrix is the product of the 2 eigenvalues. If you have a 3 by 3 matrix, then the determinant is the product of all 3 eigenvalues. Lambda 1 times lambda 2 times lambda 3. So in this case, if the determinant of H is positive, that implies that either lambda 1 and lambda 2 are positive, or that means that lambda 1 and lambda 2 are negative. If they're both positive, then their product would give you a positive determinant. If they're both negative, then their product would give you a positive determinant. So that's why if the determinant is positive, then you could have a relative maximum or a relative minimum. If the second partial derivative is negative, that means that both of your eigenvalues are negative. So that means you're looking at a concave down function, and that means you have a relative maximum. Okay, so then if your determinant is positive and your second partial with respect to x or y, doesn't matter, is positive, then that means that both of your eigenvalues are positive, and that means you have a concave up function, and that means you're looking at a relative minimum at the critical point. If the determinant is negative for a 2-variable function, if the determinant is negative, that would imply that lambda 1 is positive and lambda 2 is negative, or it could imply that lambda 1 is negative and lambda 2 is positive. In other words, they just have to have opposite sign. And so in the case where your eigenvalues have opposite sign, your determinant will be negative, and you would have a saddle point using our eigenvalue test. And so this is basically the eigenvalue test, but it is being sneaky and using the fact that the determinant is the product of the eigenvalues. Okay, so this test fails for 3-variable functions. And it fails for 3-variable functions because you would have 3 eigenvalues. And so if your determinant is positive, that means the product of all 3 of your eigenvalues are positive, but 2 things could happen. Either you have positive, positive, positive as your eigenvalues, or you could have positive, negative, negative. And either way, you would have a positive determinant. So a positive determinant could mean you have a minimum. It means you have a minimum, or you could have a saddle point. Yeah, and so that's why it fails. And then again, if your determinant were negative, then you could either have negative, 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 or you could have negative, positive, positive, meaning you could either have a maximum or you could have a saddle point. Yeah. And so this doesn't work for functions of 3 variables, but it does work for functions of 2 variables. So that's a really long way to say we are not going to do that in this class because you need a lot more time to practice, and I'm not going to make you do that. We don't have time. I wish we did, because I like linear algebra, but...
So what is the geometric interpretation of eigenvalues?
That's a good question. And I can tell you where to find that explanation. If you search 3b1b eigenvalues, It's part of his playlist on Essence of Linear Algebra. But notice that this is chapter 14 of his playlist on linear algebra, which means this is normally something that's taught towards the end of a linear algebra course. And so I wish that I had 16 weeks to explain this to you guys, but I don't. I have 23 minutes, and now we need to move on with the rest of our class.